The voltage rating of an electrical conductor represents the maximum voltage that can be safely applied to the conductor on a continuous basis without risking premature failure. This rating is typically expressed in volts. According to ISA, that is, the Insulated Cable Engineers Association standards, a voltage rating of a conductor is based on the phase-to-phase voltage of the electrical system where the conductor will be used. This is because, in a balanced three-phase system, the voltage between any two conductors equals the phase-to-phase voltage. For instance, if a three-phase electrical system has a phase-to-phase voltage of 600 volts, the conductors in that system must be rated for 600 volts. Now all, that is, Underwriters Laboratories, and NEMA, that is, the National Electrical Manufacturers Association standards, usually define the voltage rating of general equipment based on the phase-to-ground voltage of the electrical system where the equipment will be used. For example, if a three-phase electrical system has a phase-to-ground voltage of 347 volts, then general equipment used in the system must be rated for 347 volt. Let's examine the impact on ungrounded or high-resistance grounded systems. In ungrounded or high-resistance grounded electrical systems, the voltage on the conductors can exceed the phase-to-phase voltage. This is because there is no solid ground reference to stabilize the system voltage. As a result, it's crucial to ensure that conductors used in ungrounded or high-resistance grounded systems are rated for the maximum voltage that may occur on the conductors during a ground fault. To find the voltage rating of conductors, refer to the applicable ISA standards. Examples include ISIS-95.658, which covers rubber-insulated conductors for use in underground service, ISIS-98.662 concerning ethylene-propylene rubber-insulated conductors for use in underground service, and ISIS-104.696, which addresses cross-linked polyethylene insulated conductors for use in underground service. In summary, understanding the distinction between voltage ratings for conductors versus general equipment is vital, particularly when dealing with ungrounded or high-resistance grounded systems. Always consult the relevant ISA, AL, and NEMA standards to ensure appropriate selection and safe operation. When selecting conductors for electrical systems, several factors beyond just the voltage rating must be considered to ensure safety and optimal performance. These include the ampacity of the conductor, the type of insulation, the environmental conditions, and applicable codes and standards. Firstly, ampacity refers to the maximum amount of electrical current a conductor can carry continuously without exceeding its temperature rating. The ampacity of a conductor is influenced by factors such as its size, material, insulation type, and the ambient temperature. It's essential to select a conductor with an ampacity that meets or exceeds the expected load current to prevent overheating and potential fire hazards. The National Electrical Code, or NEC, provides tables and guidelines for determining the appropriate ampacity for various conductor types and installation conditions. Secondly, the insulation type of a conductor plays a critical role in its ability to withstand voltage stress, resist environmental factors, and maintain electrical integrity. Common insulation materials include thermoset polymers like cross-linked polyethylene, or XLPE, and ethylene propylene rubber, or EPR, as well as thermoplastic materials like polyvinyl chloride, or PVC, and nylon. Each insulation type has its own set of properties, such as temperature rating, moisture resistance, chemical resistance, and dielectric strength. Selecting the right insulation type depends on the specific application and the environmental conditions to which the conductor will be exposed. Thirdly, environmental conditions such as temperature, moisture, and exposure to chemicals or sunlight can significantly impact the performance and lifespan of electrical conductors. High temperatures can reduce the ampacity of conductors and accelerate insulation degradation. Moisture can lead to corrosion and insulation breakdown, while exposure to chemicals can cause the insulation to deteriorate. Sunlight, particularly ultraviolet radiation, can also degrade certain insulation materials. Therefore, it's important to select conductors that are suitable for the specific environmental conditions in which they will be installed. This may involve using conductors WITH Chinese letter insulation materials, applying protective coatings, or providing shielding to minimize exposure to harmful elements. In addition to the ICER, UL, and NEMA standards, there are other applicable codes and standards that govern the selection and installation of electrical conductors. The NEC is the primary code used in the United States for electrical installations. It provides detailed requirements for conductor sizing, insulation, protection, and installation methods. Other relevant standards may include those published by the Institute of Electrical and Electronics Engineers, or IEE, and the American National Standards Institute, or ANSI. It's essential to comply with all applicable codes and standards to ensure the safety and reliability of electrical systems. When working with ungrounded or high-resistance grounded systems, there are some additional considerations to keep in mind regarding conductor selection. As mentioned earlier, in these systems, the voltage in the conductors can exceed the phase-to-phase voltage during a ground fault. Therefore, it's crucial to select conductors that are rated for the maximum voltage that may occur under fault conditions. Furthermore, it's important to ensure that the insulation system is robust enough to withstand the end voltage stress. In some cases, it may be necessary to use conductors with thicker insulation or special insulation materials to provide adequate protection. Another important consideration is the grounding impedance of the system. High-resistance grounding systems use a resistor to limit the ground fault current, while ungrounded systems have no intentional ground connection. The grounding impedance affects the magnitude and duration of the voltage rise in the conductors during a ground fault. Therefore, it's important to coordinate the conductor selection with the grounding impedance to ensure that the voltage stress on the conductors remains within acceptable limits. In addition to conductor selection, proper installation practices are also essential for ensuring the safety and reliability of electrical systems. This includes following the manufacturer's recommendations for conductor handling, bending, and termination. It also involves using appropriate tools and techniques to avoid damaging the conductors or insulation. Furthermore, it's important to properly support and secure the conductors to prevent excessive strain or movement. This may involve using cable trays, conduits, or other support structures. Finally, it's essential to perform regular inspections and maintenance to identify and address any potential problems before they lead to failures. This includes checking for signs of insulation damage, corrosion, or overheating. It also involves testing the insulation resistance and performing other diagnostic tests to assess the condition of the conductors. By following these guidelines and best practices, it's possible to ensure the safe and reliable operation of electrical systems and to minimize the risk of electrical hazards. Remember, when selecting conductors for electrical systems, carefully consider the ampacity, insulation type, environmental conditions, and applicable codes and standards. For ungrounded or high-resistance grounded systems, pay special attention to the voltage rating and insulation system to ensure that they can withstand the end voltage stress during a ground fault. And always follow proper installation practices and perform regular inspections and maintenance to keep your electrical systems in top condition. The voltage rating marked on electrical conductors indicates the maximum sustained voltage the conductor's insulation can withstand without failure. It's a critical parameter for safe and reliable operation of electrical systems. Let's consider factors affecting this voltage rating. The type of insulation material significantly impacts the voltage rating. Materials like cross-linked polyethylene, or XLPE, polyvinyl chloride, or PVC, and ethylene propylene rubber, or EPR, each have distinct dielectric strengths and temperature ratings, dictating the conductor's ability to resist voltage breakdown. The thickness of the insulation is directly proportional to the voltage rating. Thicker insulation provides a greater barrier against electrical discharge, enabling the conductor to operate safely at higher voltages. Manufacturing processes play a crucial role. Consistent insulation thickness, absence of voids or contaminants, and proper curing are essential for achieving the desired voltage rating. Temperature has a significant impact. High temperatures reduce the dielectric strength of insulation, lowering the effective voltage rating. Conductors are therefore rated for specific operating temperatures, Environmental conditions also matters. Exposure to moisture, chemicals, and ultraviolet radiation can degrade insulation, reducing its voltage withstanding capability. Standards organizations like ISO, UL, and NEMA set testing protocols and performance criteria for conductors. These standards ensure that conductors meet minimum voltage rating requirements for specific applications. Proper conductor selection involves matching the conductor's voltage rating to the system voltage. Using a conductor with an insufficient voltage rating can lead to insulation breakdown, short circuits, and potential fire hazards. Overvoltage conditions, such as lightning strikes or switching surges, can temporarily exceed the conductor's voltage rating. Surge protection devices can mitigate these overvoltages. Insulation degradation over time gradually reduces the conductor's voltage rating. Regular inspection and testing can detect degradation before it leads to failure. Now consider the impact of harmonic distortion. Nonlinear loads can introduce harmonic currents, which increase the voltage stress on conductors and reduce their effective voltage rating. Dating factors are applied to conductors in certain conditions, such as high ambient temperatures or multiple conductors in a conduit. These factors reduce the allowable current and, consequently, the voltage stress on the insulation. In high-altitude environments, the reduced air density lowers the dielectric strength of air, increasing the risk of voltage breakdown. Special considerations may be necessary for conductor selection in these environments. Shielded cables use a conductive layer to contain the electric field within the cable, reducing stress on the insulation and allowing for higher voltage ratings. Conductors used in underground applications must be resistant to moisture, chemicals, and mechanical stress. Underground cables often have thicker insulation and protective jacketing. Flexible cables, used in applications requiring bending and movement, are designed with insulation that can withstand repeated flexing without cracking or degrading. Fire-resistant cables are designed to maintain their insulation integrity during a fire, preventing short circuits and allowing critical circuits to remain operational. High-voltage cables used in power transmission and distribution require specialized insulation materials and construction techniques to withstand extremely high voltages. Submersible cables are designed for underwater applications and must be resistant to water penetration, corrosion, and pressure. Specialty cables are designed for specific applications such as aerospace, medical, or military, with unique voltage rating and performance requirement. Now, how do standards organizations contribute? ISO, UL, and NEMA develop and publish standards that specify the voltage rating requirements for different types of conductors. These standards ensure consistency and safety across the industry. UL listing indicates that a conductor has been tested and certified to meet UL safety requirements, including voltage rating. NEMA provides standards for conductor dimensions, materials, and performance characteristics, including voltage rating. IC, or the International Electrotechnical Commission, develops international standards for electrical conductors, including voltage rating. These standards are used in many countries around the world. AE develops standards for power cables and accessories, including voltage rating. These standards are widely used in the power industry. Now let's talk about testing and certification. Dielectric strength testing involves applying a high voltage to the conductor to verify that the insulation can withstand the specified voltage rating. Insulation resistance testing measures the resistance of the insulation to leakage current. A high insulation resistance indicates good insulation integrity. Partial discharge testing detects and measures small electrical discharges within the insulation, which can indicate insulation defects. Aging tests simulate the effects of long-term exposure to heat, moisture, and other environmental factors to assess the long-term performance of the insulation. Cable manufacturers conduct extensive testing to ensure that their conductors meet the specified voltage rating and performance requirement. Independent testing laboratories provide third-party testing and certification services to verify that conductors meet applicable standards. Proper conductor handling, installation, and maintenance are essential for maintaining the voltage rating and preventing premature failure. Avoid damaging the insulation during handling and installation. Use appropriate tools and techniques for stripping, terminating, and splicing conductors. Protect conductors from exposure to excessive heat, moisture, or chemicals. Periodically inspect conductors for signs of damage or degradation. Now consider voltage drop. Excessive voltage drop can occur if conductors are undersized or if the circuit is too long. This can lead to equipment malfunction and reduce efficiency. The NEC provides guidelines for calculating voltage drop and selecting appropriate conductor sizes. Shielding is used to reduce electromagnetic interference, or EMI, and improve signal quality in sensitive electronic circuits. Grounding is used to provide a low impedance path for fault currents, protecting equipment and personnel from electrical shock. Surge protection devices are used to protect electrical equipment from voltage surges caused by lightning strikes or switching operations. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect conductors from overloads and short circuits. Electrical enclosures are used to protect electrical equipment from environmental factors and to prevent accidental contact with energized parts. Warning labels are used to alert personnel to potential electrical hazards. Safety procedures are essential for preventing electrical accidents. To energize circuits before working on them, use appropriate personal protective equipment, or PPE, such as gloves, safety glasses, and insulated tools. Follow lockout-tagout procedures to prevent accidental re-energization of circuits. Regular training is essential for ensuring that personnel are aware of electrical hazards and safety procedures. Proper documentation is essential for maintaining a safe and reliable electrical system. Keep accurate records of conductor sizes, voltage ratings, and installation details. Maintain up-to-date electrical schematics and wiring diagrams. Periodically review and update safety procedures and training materials. By following these guidelines, you can ensure that electrical conductors are properly selected, installed, and maintained to provide safe and reliable operation.